Welcome back to Nick's Algebraics. Today, my special guests are Random Guy.
Hello, I'm a random guy. That's what I was called in the first video, and since then, Nick wouldn't change it. So we're rolling with it. I'm random guy.
That's right. And we have a new guest, Jelly.
I'm Jelly. It's my first time in a video and I'm really excited. So thanks for having me.
Yay, of course. Thank you
Yeah.
for being halved. And as usual, the guided notes will be in the description. So check that out. So today I'm going to talk about LU decomposition. Imagine you're working with multiple systems of linear equations, like right here, and they all share the same coefficient matrix A, but they have a different right-hand side. The B's are all different.
There's always a but, huh?
Yeah, unfortunately. So one way you can solve for X is to use Gaussian elimination, right? You can use Gaussian elimination on each system and you can find X. And that's great. Gaussian elimination is very reliable, but it's very inefficient when you're solving systems like this with the same A but with different B. So we don't want to start from scratch every single time. A more efficient approach would be to decompose A into simpler matrices. And those matrices can be used to solve the system of linear equations. So this is called LU decomposition. So it's a method of decomposing a square matrix A into the product of a lower triangular matrix L and an upper triangular matrix U. So we're basically writing A as L times U. All right. Remember, a lower triangular matrix is a square matrix that has zeros above the main diagonal. This is the main diagonal here, and you can see there's zeros above it. And for an upper triangular matrix, it has zero entries below its main diagonal. So this is the main diagonal, and it has zero entries below it. Let's consider a 3 by 3 matrix A, and we want to decompose this into L times U. So we're trying to figure out what the entries of L and U are. Does anyone have any ideas how we're going to figure out what these entries are, these 12 entries? Any
You're
ideas?
asking us to independently derive the method.
Pretty much. So I'll just say it. So what we're going to do is we're going to multiply L and U, and that's going to give us one 3 by 3 matrix. And this equals, this 3 by 3 matrix. And we're just going to set all the corresponding entries equal to each other. All right. So you'll see that in a second.
Okay, that's not too crazy.
Yeah. So let me rewrite this matrix here. So yeah, I'm going to multiply these two matrices. I'm going to start with the first row of L and the first column of U. The upper left entry of LU is going to be what?
It will simply be like it's kind of like a dot product kind of deal here. So it's really just going to be those first two entries multiplied together. The other terms will be zero.
Exactly. It'll just be L11 times U11. This is going to be a very wide matrix, not to body shame it. So we have the upper left entry. So now let's move on to the entry to the right of that. So I'm going to do a dot product with the first row of L and now the second column of U. So what is that going to give us?
L11, U12, and then you just zeros for the rest. So
Yeah, and then the rest will be zero. So this is just L11, U12.
this is just a review of matrix multiplication.
Yeah. So now I'm going to move over to the third column.
Starting to sense a pattern here since there's just zeros for the two entries in the first row there.
Yeah. So this is going
Just
to just be L11 and U13. So now I'm going to take a look at the second row of L and the first column of U. What would this entry be?
L21, U11, and the rest are zeros.
Yeah. All right. So now let's move on to the second column of U. What would this entry here be?
It would be L21 U12 plus L22 U22.
Yeah, so now let's take a look at the third column.
It's going to be L21 U13 plus L22 U23. 0.
Yes,
We always do a derivation on this channel.
that's right.
Whereas me, I don't know if I would bother.
I could have just given you guys the formulas and just said, hey, let's apply these, but I want you guys to understand what's going on at a deeper level.
Given your major, that's insulting to me. No major reveal in this video. That's for 100,000 subscribers, maybe. I don't know.
Yes,
It's not what you think, dear viewer.
you might be surprised. Okay, so now for the third row of L and the first column of U.
It's L31 U11 plus 0 plus 0.
Yes. Okay, now for the second column of U.
Slightly spicier, fewer zeros. So we're going to get that L31 U12 plus that L32 U22 plus 0.
Yes.
We love zeros in our matrices.
We do love a sparse matrix. All right, so for the last entry with the third row of L and the third column of U, what is that going to be?
L31 U13 plus L32 U23 plus L33 U33.
Yeah. Okay, so great. We multiplied L and U. So now we have these two 3x3 matrices equal to each other. Now I can just set each corresponding entry equal to each other. And that will result in this system of equations. And how many unknowns does this system contain? Because we know A, we know all these entries.
We just don't know the L's and the U's in those two matrices, don't we?
Exactly. Yeah, that's what we're trying to find. We're trying to decompose A into L times U. So we don't know any of the L and the U entries. So how many total unknowns is that?
12.
You're right. There are 12 unknowns, 6 for L and 6 for U. So that's 12 unknowns. And how many equations do we have?
We can count 1, 2, 3, 4, 5, 6, 7, 8, 9 equations.
Yeah, we have 9 equations, one for each entry of this 3x3 coefficient matrix. So that's
How many are to count them individually?
All right. So we got 12 unknowns, 9 equations.
That is a problem.
Yes, this means that the system is underspecified. And
Ooh, vocabulary.
yes, we have more unknowns than equations. So that tells me something interesting. That means there are infinitely many L's and U's. That means the LU decomposition of a matrix is not unique. There are yeah,
free variables.
yeah, there are some free variables. So you're not going to get a unique L and U for a given matrix. What I'm going to do to resolve this is I'm going to impose 3 additional conditions. Since we have 3 more unknowns than equations, we need to specify 3 of the unknowns to make the system solvable.
Oh, I can't wait to figure out how you're going to fit that in.
Yes, what I'm going to do to make this system solvable is I'm going to specify the diagonal elements of L to be 1.
Somehow I knew it was going to be something dumb like that. You're just going to define it to be a certain way so that it works.
Exactly. So that means L11, L22, L33, they're all going to equal 1. So these diagonal entries are all 1 now. And this is called Doolittle decomposition.
And that's really what it's called, huh?
Yep. I could have made the diagonal entries of U all 1. That would be called Kraut decomposition. But Doolittle decomposition is when you set the diagonal entries of L equal to 1.
And if you let it vary freely, then it's called Nick decomposition.
Yes. That's the official terminology.
You better believe it is.
All right. So with these conditions, we now have 9 unknowns because we had 12 unknowns and I just specified 3 of them. So we're down to 9 unknowns and 9 equations. So that makes the system solvable. Okay, great. So what I did here is I just copy pasted this and I just set L11, L22, and L33 equal to 1. And that will give you this system of equations.
Could you point to where those entries were?
Right here.
Ah,
Yeah.
I see.
Right here. Right here. So all of those are 1.
Okay.
And that results in this. So now I can solve for all the L and U entries. So for the first 3 equations, that's kind of already done. We know A11, we know A12, we know A13. So we automatically know U11, U12, and U13. So basically the first row of U is equal to the first row of A. So that's nice. And we know U11 now, but we don't know L21. So how am I going to solve for L21? What do I got to do?
Well, we know A21, don't we?
Yeah, we know all the A entries.
You just divide that sucker, you know?
Exactly.
This is an Algebra 1 equation. This is a pre-algebra equation.
Yes, we love those. They don't call it linear algebra for nothing. So I'm going to divide by U11. So I get L21 equals A21 over U11. So again, we know U11. We know that's just equal to A11. But we don't know L31. So we're just going to divide by U11 again. So you just get L31.
Are we going to do all of these? Or like, are you just going to show us in the next page that you have it all worked out already?
No, I'm going to show it all. There's only 4 more.
Okay, we can speed run it.
Okay, we know L21 now over here. We know U12, that's over here. So we just don't know U22. So how am I going to solve for that?
You just subtract.
Exactly. So we're just going to subtract this term here. So we get U22 equals A22 minus L21 times U22. All right. And for the next one, we don't know A23. So same thing, I'm going to subtract. U23 equals A23 minus L21 times U13. All right. And we now know U22 from here. We know U12 from here. We know L31 from over here. So we just don't know L32.
Well, we subtract and we divide.
Yeah. So when you do that, you're going to get that L32 equals A32 minus L31 times U12 divided by U22.
Probably a bit late to mention this for people who don't already know, but these subscript numbers are not like 32, 31, 12, or anything like that. It's like row number, column number, but it looks like the numbers are like 32 and stuff.
Yeah, A32 is the entry of the coefficient matrix A in the 3rd row, 2nd column. Okay, and then lastly, we don't know U33.
Subtract.
Yes, we're going to subtract these 2 terms. So U33 equals A33 minus L31 times U23 minus L32 times U23. So we now have all the L and U entries. So that's great.
It's very anticlimactic.
Yeah, a little bit. But here is what we've all been waiting for.
Oh, yay.
Yeah, Doolittle, decomposition. So here are all the formulas. If you didn't listen to anything in this video, this is what you've been waiting for. These are the formulas for Doolittle decomposition to find.
How short could the average Algebraics video be if we just didn't do the derivations?
That's a good point.
But no, you gotta know where it came from.
Yes,
Helps you remember how to use them.
exactly. And you have to do it in this order because you have to unlock some specific entries first, and then that will unlock different entries.
So you have to do step 1 through 5 in that order, you say.
Yeah, that's Doolittle decomposition. These are the formulas we're going to use. Okay, so that's just decomposing A into L and U. But the goal is to find X. We're trying to solve AX equals B here.
But yeah, I forgot what we were doing all this for.
So once A is written as L times U, solving ax equals b becomes a two-step process. So first, let me write this out. So we know ax equals b. That's what we're given. We're given a system of linear equations. I just wrote a as L times U. So LUX equals B. What I can do is I'm going to let UX equal Y. So we now have LY equals B, and UX, I just said, is Y. So basically what I did is I got this complicated system of linear equations and I broke it up into two baby systems of equations. Now these are very easy to solve because it's just a lower triangular matrix and an upper triangular matrix. So for Ly equals B, you just have to use forward substitution. And for Ux equals Y, to solve for X, you just need to use back substitution. It's just a baby system of equations now. That's what we got to do. We're going to write A as L times U. We're going to solve Ly equals B for Y using forward substitution. And then we're going to solve Ux equals Y for X using back substitution. All right. So let's do an example. So using an LU decomposition of the coefficient matrix, the coefficient matrix is just A, solve the linear system.
Maybe we should start by writing the coefficient matrix.
Yes, that's a good idea. So we have A equals, give me the entries for the first row.
1, 2, and -4.
Yeah.
I guess I'll do the second two. I'll say it's 5, 11, and -21.
Yep. Yeah, and then you can just say the last row.
3, -2, and 3.
Exactly. Good.
Period.
So that's the coefficient matrix. Okay, so now let's figure out what L and U are. So I'm going to use these formulas here. So first step is finding the first row of U. So U11 is just A11. And what's A11? What's the entry in the first row, first column?
That would be numero uno.
Yes. U12 is just A12. So what's the entry in the first row, second column?
That would be numero dos.
Yes. And U13 is just A13. And what is that?
That would be -3.9 repeating.
Yes, -4.
Only the real viewers will get that one.
Yeah. Okay, so great. We got the first row of U. So now let's find L21 and L31. So L21.
Do you want to refer back to the steps so that people can see what you're doing?
Sure. I'm just using these formulas in this table. So I'm going to use these formulas now. So L21 is just A21 divided by U11. What is A21?
5.
Yes. And then U11 we just figured out right here. That's 1. So we have 5 divided by 1. What does that equal?
5 divided by 1 is 5.
Yes. Good. All right. So now let's do L31. So if you look at my table, you'll see that that equals A31 divided by U11.
Do you have these formulas memorized, Nick?
Yes.
Period.
So what is A31?
3.
Yes. So, and then U11, we did that earlier. That's just 1. So we have 3 divided by 1. And what does that equal?
3.
Yes, 3. Okay. Now for the third part is we need to find U22 and U23. So again, we're just going to apply these formulas. Number 3. So U22 is just A22 minus L21 times U12. So A22 is 11. So we have 11 minus L21. We just did that here. That's 5. U12 is 2. So we have 11 minus 10. That's just 1. And now let's find U23. So that's just A23 minus L21 times U13. So A23, that's just negative 21. And L21 is 5. And U13 is negative 4. So that's just negative 21 plus 20, which is just negative 1. All right. And now for part 4, we need to find L32. L32 is A32 minus L31 times U12 over U22. So A32, if you look at this matrix, is just negative 2. And L31 is 3. U12 is 2. And U22, we just found that is just 1. So we have negative 2 minus 6 divided by 1. That's just negative 8. All right. And then the last unknown entry
Finally.
is U33. So U33, that equals A33 minus L31 times U13 minus L32 times U23. So A33 is just 3 minus L31 is 3 also, and U13 is negative 4. So we have 3 times negative 4, and then minus L32 is negative 8, and U23 is negative 1.
This is such a thankless task.
It is. It's very thankless. But if you do all the arithmetic here, you're going to get 7. We now have L and U. So let me just create that. So L, remember, lower triangular matrix has zeros above the main diagonal. Since we're doing Doolittle decomposition, we have ones on the main diagonal. So 1, 1, 1, and we have 0.
What was the other one? Kraut, was it?
Yeah, because Kraut is when the upper triangular matrix has ones on the main diagonal.
Sauerkraut?
Yeah. So by default, we have this. So we just figured out the other entries. We have L21 is 5, L31 is 3, and L32 is negative 8. So we have 5, 3, negative 8. And for U, it's upper triangular. So we're going to have zeros here below the main diagonal. And we have all the other entries. So we know the first row is 1, 2, negative 4. It matches the first row of A. So 1, 2, negative 4. We have U22 and U23 is 1, negative 1. And the bottom right entry is 7. Okay, that's great. And you can verify, you can multiply L and U, and you'll see that you get A.
You're not going to do that, I hope.
Oh, no, I'm not going to. I'm not going to do that. That's enough matrix multiplication. So remember, after we write A as L times U, now we have to solve 2 baby systems of equations. So we're going to solve Ly equals B for Y using forward substitution. So we have Ly equals B. So we have L. I wrote that here. Y, we don't know what that is. I'm just going to say this is Y1, Y2, Y3. And what's B?
That would just be the right side of the equations.
Exactly, just those constants. So it's negative 7, negative 38, 17. Okay, so now we have a system of equations. We're going to use forward substitution here. It's forward substitution because we're going to start at the top. So if you multiply, you're going to get 1y1 is negative 7. So that just means y1 is negative 7. And then over here we have 5y1 plus 1y2. So just plus y2. That equals negative 38. We know y1 is negative 7, so we have 5 times negative 7 plus y2 equals negative 38. And if you solve for y2, you're going to get negative 3.
I'm sure Nick has an equation solving channel video somewhere, about how to do this type of equation.
Yes.
Earlier videos. It's probably an hour-long documentary on how you would solve something like this.
Yes, check out my early videos on how to solve one-step equations. Okay, and then for the third equation, we have 3y1 minus 8y2 plus y3 equals 17. So 3y1 minus 8y2 plus y3 equals 17. And I'm going to plug in y1 and y2. If you do the arithmetic, you'll get that y3 equals 14. So that's our forward substitution there. So now remember, y is ux. So ux equals y. We know u. We're trying to find x. That's really what we want. So x1, x2, x3. And then y, we just figured out what that is. We know y1 is -7, y2 is -3, and y3 is 14. So we got -7, -3, 14.
This is just another system of equations.
Yes, another baby system of equations. And now we're going to use back substitution because we're going to start from the bottom. So we have 7x3 equals 14. So that means x3 is 2.
Yeah, you got to show the steps. You divide both sides by 7. And you cancel it out.
Oh my. And then for the second equation, we have x2 minus x3 is -3. So x2 minus x3 equals -3. And x3 is 2. So we have x2 minus 2 equals -3. And if you add 2 to both sides, you get x2 is -1. Let me box these because these are actually the final answer. And lastly, the next equation is x1 plus 2x2 minus 4x3 is -7. So x1 plus 2x2 minus 4x3 is -7. x2 is -1. x3 is 2. And if you do the arithmetic, you'll get x1 equals 3. And that is our solution, 3, -1, 2.
I feel no sense of satisfaction from this whatsoever. Shelly, what do you think about this? How did you find this lesson?
10 out of 10 would recommend.
Perfect. That's what
I can see why you would want to use it. I can see why it's useful. I just don't have to like it.
maybe.
Isn't this supposed to like solve the fact that it would be less efficient to do it a different way using like Gaussian elimination?
Yes, the reason why we're doing this is because back to the original problem, if you have the same A for a bunch of systems of equations, but different B's, you don't want to use Gaussian elimination on each one. That would take forever. So instead, we can write all these A's as L times U, and we can just do a bunch of forward and back substitutions. So because
we could use the backslash in MATLAB and you can do it instantly.
That's true. But this decomposition significantly reduces the computational cost because L and U need to be computed only once. But just for fun, just for funsies, let's find the determinant of A.
So, okay, that's not too bad. Are we going to use the cofactor or?
Well, we know A is L times U. So that means that, yes, the determinant of A is just going to equal the determinant of L times the determinant of U. And what is the determinant of L?
You just multiply them diagonals together.
Yes, the determinant of a triangular matrix, whether it's upper or lower, is just the product of the entries on the main diagonal. And since we're using Doolittle decomposition and I defined the entries on the main diagonal of L to be 1, that means the determinant of L is just 1 times 1 times 1, which is 1. So really, the determinant of A just equals the determinant of U. And the determinant of U, again, it's a triangular matrix, so we just have to multiply the entries on the main diagonal. So we have 1 times 1 times 7, so you get 7.
This is the most satisfying thing that's happened during this video.
Yes. That's another...
It ties back to a different lesson you did.
Exactly, yeah. Anyway, let's do one more example.
Oh, no.
This one is a little different. I purposely did this example to prove a point.
I love those kinds of examples. Let's do it.
Yes. So use an LU decomposition of the coefficient matrix to solve the linear system. So let me write the coefficient matrix. So what does A equal in this case?
0, -6, 4 for the first row. 2, 0, -14 for the next. and -1, 4, and 3 for the last.
Perfect. Let's use those formulas again from this table here.
It's the best part.
Yep. For the first row of U, we know U11 is just A11, which is 0. U12 is -6. It's just A12. And U13 is 4. It's just A13. And then for the second part, we need to find L21. So remember, if we go back to our formulas, L21 is just A21 divided by U11. So if you do A21, that's just -6, divided by U11.
Oh,
What,
interesting.
what's happening here? It looks like we have a little bit of pain.
This
So,
is a doozy.
yes, it's a
Doolittle doozy.
it's a Doolittle doozy. So it turns out that this matrix does not have an LU decomposition.
Aw.
So let me just write A.
You mean we don't get to do the rest of the steps?
You'll see what I'm going to do. A does not have an LU decomposition. Here's what I'm going to do. I'm going to use something called row pivoting. I'm going to get this matrix. The problem is that the top left entry, the A11, is 0. That's the problem because we're dividing by U11, which is A11. So, okay, that's fine. I'll just use row pivoting. I'll just swap the first two rows.
You
And
you gave it such a fancy name, but it's nothing special.
I'm just swapping rows just to get the maximum entry in that pivot position, basically. So let me just write the system of equations now. We have ax equals b. X is just x1, x2, x3. And since I swapped the first two rows, I need to also do the same thing for b. So that becomes 34, -14, and -5.
Was the row pivoting the point that you were going to make with this example?
Yes.
That was it?
Yeah, that was it.
Oh,
And
disappointing.
just so there's no confusion, let me call this a prime, just because I'm using a twice. Anyway, but I just swap the first two rows and I get this equivalent system of equations. I have a different coefficient matrix and I'll just do LU on that and I'll solve the system and I'll get the same answer as this. All right, so we're avoiding that division by 0 for L21. All right, so let's figure out those entries again. Now that we have all the LNU entries, now I need to solve Ly equals B using forward substitution. So L, we have ones on the main diagonal. We got zeros here because it's lower triangular. And let's see, we have L21 and L31, that's 0 and -1/2. And L32 is -2/3. And Y, I'm just going to say that's Y1, Y2, Y3. And what is B?
Oh, that is simply. Oh, but didn't we flip it around because we did like the row stuff?
Yes.
Rows. So now it's 34, -14, -5.
Yeah. So just be aware of that. That's another point is to avoid division by 0, we did that row pivoting and we also swapped the rows of B. So just make sure to use that B and not the original B. Okay. So another baby system of equations. So we have 1y1 is 34. So that's just y1 equals 34. And then over here we have 1y2 is -14. So that's just y2 equals -14. And then over here we have, okay, we have -1/2 times y1 minus 2/3 y2 plus 1y3 equals -5. All right, so we know y1 and y2, so let me plug that in. We know y1 is 34. We know y2 is -14. So if you do all the arithmetic, you will get that y3 is 8/3.
The fraction is an L for sure.
It is. Now let's solve for x in ux equals y. So u It's upper triangular, so we're going to have these zeros here. We know the first row of U is the same as the first row of A, the swapped A, of course. So 2, 0, negative 14. And U22 is negative 6, U23 is 4, and U33 is negative 4/3. And this is times X, so this is X1, X2, X3, which is what we're trying to find. Remember, don't lose track of our end goal. And then and then y we just figured out. It's 34, negative 14, and 8/3. So we're going to do back substitution. So we're going to start from the bottom. So we have negative 4/3 times x3 equals 8/3. So x3 is just going to be negative 2. And then for the second equation, we have negative 6 times x2 plus 4x3 equals negative 14. And we have x3, so we have negative 6x2 plus 4 times x3, and x3 is negative 2. And that equals negative 14. And if you solve for x2, you'll get 1. And now we're going to write one more equation. So we have 2 times x1 minus 14x3 is 34. So 2x1 minus 14x3 equals 34. And x3 is negative 2, so 2 times x1 minus 14 times negative 2 equals 34. And if you solve for x1, you get 3. So that's our solution, is 3, 1, negative 2.
Yeah.
Yay.
I'm so happy.
Yep,
The happiness is overwhelming.
it is. And just for fun, let's do some determinants as a reward. So let's find the determinant of the original non-swapped matrix, A prime. The determinant of A prime. How are we going to figure out what that equals?
You would simply take the answers we got and take the diagonals, and then you do some math.
Well, that would be for A. That would be for this matrix. That
Oh, for A.
Yeah,
for A prime.
Yeah, for A prime, how does the determinant of A prime relate to the determinant of A? What happens when you swap two rows?
Ooh. You put a negative sign down.
Yes, when I swap two rows of a matrix, I need to introduce a negative factor in front of the determinant. So this is equal to the opposite of the determinant of A.
This is from that determinant video we did.
Yes, check that out. And we know about A. We did the LU decomposition on that matrix. A is just L times U, so the determinant of A is just determinant of L times the determinant of U. And what's the determinant of L?
Let's take a look at L. Oh, it's just 1.
Yeah, because we're doing Doolittle decomposition, it's just going to be 1. So really, we're just looking at the determinant of U. And that's just, again, the product of the entries on the main diagonal, because it's an upper triangular matrix. So 2 times negative 6 times negative 4/3. So we got negative, because we swapped rows, 2 times negative 6 times negative 4/3. And this is just negative 16. The problem didn't ask for it, but I'm giving it to you anyway.
Didn't you write these problems?
I did.
You always like speak of the person who wrote these questions in like the third person, somewhere in the sky, some cloudy figure who just came down on high and gave you these problems as if it's not you.
Yeah, I don't know. It's a habit. Anyway, but I have one last thing to talk about. That's our last example of today. You're probably wondering, Nick, every example you did is just for a 3x3 matrix. But what if I want to do LU on a 4x4 or a 10x10? Because
I'm gonna be honest, I was not wondering that one bit.
I was.
Perfect. So here are the general formulas for an n by n coefficient matrix for Doolittle decomposition.
We're not doing examples, right?
I'm just showing you this. If you want to use it, you can pull up MATLAB or whatever programming language and type these formulas in and have the program do it for you. That would be the best way of doing it. Yeah, if you have anything more than a 3x3, doing it by hand is going to take forever. So these formulas are here for the computer science majors and the engineers. But that is it for today. Don't forget to like and subscribe. And thank you guys for sticking around.
Comment.
Yes, please comment. And I will.
For the 2 people who made it this far, leave a comment.
Yes, please. And I will see you guys in the next video. All right. Bye.
Bye.